general relativity, step by step. Last time I cast the Einstein field equations into this form here, using the stress energy tensor T all mu nu, which was equal to T mu nu plus the cosmological, or plus the vacuum energy, mu nu vacuum. And I asserted that that was equal to T mu nu minus cosmological constant over 8 pi g upon c to the 4 g mu nu. And now I'm going to work on these and work out what they are and how to express them for different cases, different circumstances. You're going to need to know GRSS, the original Trintragular playlist, numbers 79 through 83 for 4 velocity, and also numbers 93 through 109 for the stress energy tensor. That's prereq knowledge for this screencast here. So what you find in this sequence here is that the stress energy tensor T mu nu equals, for a perfect fluid, which is characterized by its density and P0. These are values in its rest frame, I guess. And what was the formula for that? That is rho 0 plus P0 u mu u nu plus P0 g mu nu. And that's a valid tensor equation. So what we have for the total stress energy tensor is equal to rho naught plus P naught u mu u nu plus P naught g mu nu minus the cosmological terms, 8 pi g upon c to the 4 g mu nu. And of course what I'm going to do is to factorise these two terms here. Now I may as well be consistent. Rho 0 plus P0 u mu u nu plus P0 minus cosmological constant over 8 pi g over c 4 g mu nu, where these things here are my 4 velocities. Now what I'm going to do is to evaluate the 4 velocity at some particular point. Here's me, there's me in my galaxy here, and here's my friend who lives in a kind of barred galaxy. There he is, and he's a sort of squiddy alien here. And what I'm going to do is I'm going to make the observation that he's at a particular distance r, a particular co-moving distance r, and so his world line is t, r, theta and phi. But these three guys here are constant. By construction, we went to a huge amount of difficulty to find a coordinate system for the whole universe in which the observers were at rest. And what at rest means is, what at rest means in this coordinate system is that these three values here are constant. The co-moving distance is constant, even though he's receding. Rn is changing. Theta's constant because he's not moving across the sky, and phi is constant because, again, he's in the same position, angular position for me. The only thing that's changing here is t, and by construction, time, this coordinate t for him, is just his wristwatch time. It's just his proper time. I say wristwatch, but he might not have wrists, he might have a tentacle watch time maybe. And so his 4 velocity is just 1, 0, 0, 0. Well, that's it, 1, 0, 0, 0. Well, that makes evaluating this thing here a lot easier. So let's just try doing that. We've got rho 0 plus P0 times, well, you see, it's only the first component that's 0, so mu and nu must both be corresponding to the time coordinate. So it's multiplied by this 16 numbers here, of which only the time coordinate, this one here, is non-zero, plus P0 minus cosmological constant over 8 pi g upon c to the 4 times the stress energy tensor. Now, what we've been using up to now, or certainly what I used in GRSS, what numbers was it? Up to number 109. I've been using the Minkowski flat space metric, but that's not appropriate here. If I go back to the Maxima session here, I can remind myself these are all the Christoffel symbols. The metric tensor I've been using is this guy here. It's diagonal, which makes our lives a little bit easier. But this one here is the metric tensor G with L for lower or downstairs indices. It's the one with that, with two covariant indices. Blom, 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 blom. So let me just minimize that. And so the numbers I've got to multiply this guy here are -1, 1 over a of t squared. Actually, I'll write it out in a little bit of a better notation. A of t to the power -2, zeros, 0 there. Just remind myself what it was. We've got a q and an a there. So that's q of r to the -2, a of t to the -2, zeros, 0, 0, and that's q of r to the -2, a of t to the -2, and this one had a, oh, it keeps on flicking out, sine squared, and it's 1 over sine squared, so it's cosec squared theta. Is that everything? Yeah. Well, that's quite a nice little formula there. It's got 1, 2, 3, 4 non-zero components, but these terms here are quite hard. Remember, this was t mu nu. So what I'm going to do is I'm going to lower one of the indices in the interest of a simple life, and I'm going to do that right now. So part of the beauty of this system is that this is a valid tensor equation, so I can just fool around with it and change it from upstairs indices to downstairs indices, and change it from one coordinate system to another as I wish. Okay, so let's just try that. I'm going to have my t mu nu, and I'm going to lower one of the indices. I'm going to lower the second index like that. It doesn't matter because it's symmetrical, and that equals, let me pinch in a little bit. Let me just write it out. Rho 0 plus P0 U mu U nu G mu nu plus P0 minus gamma over 8 pi G upon C to the 4 G mu nu G with downstairs indices. Oh, I've got a nu down there. I'm killing both of them. I just meant to kill one. Mu alpha. Mu alpha. Well, that's dead easy. We can do that one. That's just a Kronecker delta times mu and nu, which is again a tensor. I'll just write it in. P0 minus 8 pi G upon C to the 4. That's a plus. Now what's this thing here? Well, we need to remind ourselves what the 4 velocity is, and the 4 velocity, I think I've got it written down here. Just a minute. That, I should wake it up again. Yeah, the 4 velocity was just 1 and 0, 0, 0. So the only component we have to worry about for these is mu equals nu equals alpha, I guess, which equals 0. So that's the only component of this guy that we've got to consider. And in that case, the value that we have is rho 0 plus P0 times minus 1, I guess. And that corresponds to T mu alpha. There we go. So T00 equals that, this component here. We've got these other components here as well. Yeah, let me just write them out. We've got T0, 0. Everything's diagonal because that bit's diagonal and this bit here is diagonal as well by construction. So we've got T00 equals minus rho 0 plus P0 for this term here, plus P0 minus gamma over 8 pi g over c to the 4, which equals, the p's cancel, minus rho 0 minus gamma over 8 pi g over c to the 4. It's a lambda. I've been saying gamma. It's a lambda, isn't it? Okay, and what about... Oops. Sorry about that. I had a bit of a glitch with my computer system there. Yeah, and we've got the other ones. T, let's just say I, where I can take the values r, theta, and phi. This first term doesn't make any difference. And the second term, it's here, it's this one here. So it's P0 minus lambda over 8 pi g over c to the 4. Well, that's it, because the Kronecker delta is equal to 1. That is equal to 1 or 0. 1 if mu equals nu, and 0 otherwise. So the only components we've got to deal with are these. So we've got these very, very simple systems. We've got T00 equals minus rho 0 minus lambda. I've been saying gamma for so long, it's hard to change my habits. And the other components, Tii, are equal to P0 minus that over 8 pi g upon c to the 4. There we go. So that's my expression for the stress energy tensor. Oh, this is the total stress energy tensor. Stop there. Stop.